Madam, shall we start?
Yeah.
Yeah. Thank you so much. Welcome all back to the electrochemical workshop, and it's our third day. Last 2 days, we discussed more the basics of electrochemistry, and the last class, of course, the electrochemical techniques. And today, we are we are going to discuss on the electrochemical impedance spectroscopy, and we have Dr. Shruti Suryakumar, and Shruti madam will take other couple of sessions, the coming sessions too, especially battery topic she's going to handle. So let me introduce Dr. Shruti to all participants. Um, Dr. Shruti madam did his PhD from ISER Sikri Karaikudi in physical science, and she got the best PhD thesis award in physical science 2020 by SESAR. And then she moved to ISER Trivandrum for doing her postdoctoral research, and she joined as Institute Postdoctoral Fellow, and then she received a National Postdoctoral Fellowship from DSTS ERB Government of India, and now she's working as the project scientist at ISER Trivandrum. And she published more than 20 international peer-reviewed journal, and there are so many awards and prizes in her credit. So with this short introduction, I'm welcoming Dr. Shruti Suryakumar to our event. Welcome, madam, and the floor is yours.
Thank you. So good evening, everyone. This is Shruti here. So I'll be handling this session on electrochemical impedance spectroscopy. So I'll just share my screen with you. Yeah, I hope my slide is visible to all of you. We've been. So before I begin, I'd like to thank CS. It's a wonderful opportunity, and I believe like for the entire spectrum of electrochemistry has been covered by them, and they've brought in different experts. And even for the past 2 days, I hope all of you have benefited from the introductory electrochemistry sessions. And I will be dealing basically about electrochemical impedance spectroscopy. I'll give you a brief introduction to it, and then we'll see how we are progressing, and then we'll try to see if we could do some data analysis and so on and so forth in the days to come. So electrochemistry, as all of you know, is kind of a very hot topic in the recent days, be it the batteries we use, be it the paint applications that we have, be it the biosensors that we find electrochemistry everywhere. And I hope a majority of the audience here are involved in one type of the other of the research based on electrochemistry. And it's basically that you have a material based on the charge transfer. A material could be converted to another material, and in the process, if there's an electron transfer happening, or it could be the other way. You could apply a potential and then convert a species from A to B. And these are the two broad aspects of electrochemistry. And we have different tools to understand it. Say, for example, if I have a battery material, I can do a charge discharge study. If I have a water splitting catalyst, I can do a HER OER study. For sensor sensitivity, we do different chronoamperimetry measurements and all. So when we are doing this in the process, we are kind of seeing what is happening to the material, whether it's being converted properly, whether it's getting oxidized, or whether it's getting reduced. And we use different techniques. We use NMR, we use XPS, we use post-cycling SEM, RAM, and all of that to see what has happened to the system and how well our system is behaving, apart from our electrochemical current voltage response and so on. So electrochemical impedance spectroscopy is one such tool, a very strong tool in its own way, which I will discuss in detail. But before I go in, I would want this session to be a little interactive. So I've been listening to a lot of the past 2 days lectures, and I know that most of you have a lot of concerns regarding electrochemical impedance spectroscopy. And so I just decided that I would start with the basics for now. I'll start with the basics and we'll go on depending on how we respond, and we'll see how the discussions are going forward. So for now, I would not want to hear your doubts. Rather, I would post some questions and I would want to listen to your feedback. So probably I hope all of you have this emojis there in the screen below you. Can all of you give me a thumbs up so that I can see a response from your side? Okay. Yeah. Okay. Okay. That's good. That's nice. Uh, I see a question raised. Yes, if anyone wants to ask a question, yes, please. Okay. Okay, now, I know that there is a half of a population who's already been working on electrochemistry, and a half of you who are completely new to it. So I would want to know, okay, I would want to know how many of you have done an EIS measurement before. How many of you, give me a thumbs up to all those of you who have done an AIS measurement before and are quite familiar with, okay, quite a few. How many of you here are completely new to impedance and you have never done an impedance measurement before? Okay, I can see an equal population on both sides. So I'll try to start with the basics. And when I wanted to start this impedance spectroscopy program, I've been looking into a few videos and I've tried to see how I would project impedance spectroscopy. Because electrochemical impedance by itself has a lot of components. It has electrochemistry in it, it has impedance in it, complex numbers associated to it, functions associated to it, different max associated to it. And I wanted to make sure that I convey it to you in such a way that I would find it easy to understand. So this video, this whole session is based on such a way that I would, at the end of this talk, you will be able to analyze and understand the spectrum that is given to you, and you will be able to interpret it on your own. So that is my whole objective, and let me see if I could satisfy that. So this is going to be the introduction. So you have, I'll be giving an introduction to EIS, what it is, and I'll give you two basic plots, the two common plots that you have, the Bode plot and the Nyquist plots, and then we'll be discussing some equivalent circuits, and then we will also have some data analysis and a common example that we have for different electrochemical chemistry fields. I would want you all to have I would want you all to have a paper, a calculator, and a pen with you for doing a rough work. And as I go forth, I would have this a little bit of interactive. So let's begin. When you look at this picture, I want you all to tell me what comes to your mind first. So you can write in the chat box if you would, if you could please. So when you look at this picture, what is the first thing that comes to your mind? Okay, I can see a concert. Okay. Music, perfect. Okay. Orchestra music. Okay. Okay. Enjoying life. Yeah, that's true. Band playing music. Okay. Yeah, fine. Good. That's good. So the thing is, all of you are able to, when you look at this image, the first thing that you're able to associate it to is a good music. Okay, I hope all of you agree with that. So as an audience, when we look at these concerts and when we look at music, we look at the output as such, whether it's a melody, whether it's a fast beat, and so on and so forth. So the output for us is a music. But when you look at it in a composer's point of view or in a sound engineer's point of view, they, yeah, as a few of you have rightly pointed out, they would look at it in terms of frequencies. So you have, and we hear it as song, but they hear it as frequency. We have low pitch, we have high pitch, we have overtones, and then each of these C, D, E, all of these majors and minors are all associated with different frequencies, and they work on that. So for us to get a good music, they just not only compose a tune, they would also be working on all of these aspects too. So to study a music, it is very necessary for us to deconvolute that music to different frequencies and different overtones and pitch and all that, and then kind of understand what is happening in the music rather than just listening to it. In the same fashion, when we look at an electrochemical phenomena, So over here you can see a battery, or you can see any other application of your choice. When you look at an electrochemical phenomenon, the output that we get is a current or a voltage response, or if it could be light sensitive. So you apply light and a material is getting activated and you get an output voltage for it, or it could be any other property. So when we look at it, we just see that you are getting an output current or an output voltage, but what happens inside it is a major concern. So electrochemical phenomena are not just concerned with one particular process. When I say that a battery is working, or when I say that there's water splitting, or when I say that there's a corrosion inhibitor, different kinds of processes are involved. To begin with, can somebody tell me what are the different processes? Or maybe okay, I'll start with it. So we have ions. We could have an electrolyte system, and an ion would be moving inside it. So an ion moving inside an electrolyte system will undergo a different process. Similarly, say the same ion, when it is given inside a bulk, say for example in a
Madam, you are muted. Still,
now.
yeah, now it's fine. Yeah, yeah.
Okay, where did I stop? Probably this slide.
I mean, just a couple of seconds. That's it.
Okay,
Yeah.
okay. Yeah. So, as I was saying, there are different processes. We have ions moving inside the electrolytes, and then we have bulk and grain boundaries, where an ion in a solid will be facing even a little more of difficulty in moving. And then there could be absorption of species onto the surface that are responding differently. And then there could be a quick double layer formation when you're having an electrode dipped into an electrolyte. So when you look at all these processes, you understand that there are a few processes that are a fast process, and a few of them are slow. Say for example, ions can move easily inside a liquid electrolyte, and that could be a fast transfer. And an electrode an electron from an electrolyte to an electrode could go through a charge transfer process that could take a significant time. Adsorption could be again a fast process. Double layer formation could again be a very instantaneous process. So all of these processes are associated with different times, and to be more scientifically correct, I could use the word time constants. So each of these reactions that I've plotted here, and many more to come, will all be associated with a different time constant. So when I look at them at a different frequency range, I would be able to segregate each one of them separately. So at a very slow, if I could give a very slow frequency, I might be able to see what is happening at the electrode electrolyte boundary, wherein there could be a charge transfer. And maybe if I go to a higher frequency range, I could look at the double layer formation. So the key to this whole impedance spectroscopy is that at different frequency domains, different reactions can happen, and that way I will be able to segregate different phenomena. So I hope that's clear for all of you. And now, when I look at EIS as such, EIS is good because one, it is a very non-destructive analysis technique. Even when your system is running, even when we are doing a measurement, you would be able to see what is happening, how are the electrodes, how is the electrolyte resistance, is there any decomposition happening, or is there any passivation film forming. All of that could be understood even while the cell is running. So that is the key advantage of impedance, and it is very less time consuming. So we are operating from a few megahertz to a few millihertz. So probably within like if you're operating from a few 1 hertz to 1 mega, so it would be finished in 2 or 3 minutes. So it's that fast, and it is also, as I said earlier, it could be used to identify different phenomena occurring at different time scales. So these are the main advantages. And as I said, these are applied to a wide range of electrochemistry research area, including corrosion studies, even for semiconductor studies, wherein you have your IV curves, and then you have energy conversion storage technologies, even for chemical sensing, biosensing, and even for few diagnostic techniques. All of this impedance spectroscopy is used. By the end of this talk, I would want to be able to make sure that I convey that if you're looking at a plot like this, I feel like I would be able to uh, make you interpret what this plot would be, and what would different semicircles or different plots in a Nyquist plot be ascribed to. So that is the main objective of the talk. I can give you these are the references. I have looked into a couple of electrochemistry videos, and this is one of the recent reviews that I came across in ACS Measurement Science Gold. So it's electrochemical impedance spectroscopy tutorial. So this is one main tutorial that you could go back and refer to. And as usual, we all have our textbooks. All of those of you who have attended courses would know that McDonald's textbooks are there available, and then there are a few YouTube videos also. So you could go back and have these as your references to look at EAS and revise your subject later. So before moving to the main part, I would, as I told you, the EIS is involved, it has a lot of constituents in it. So I would want to revise, and since many of you are new to this entire field, I will give you a little bit of basic max and waves and phase diagrams. And from there, we'll go to circuit elements, and then we will move on. I hope it's okay for all of you if I'm going at this phase. So what you're looking at is a sine wave. So this is a sine wave. If you could look at it, one cycle is, say, 1 second. So one complete cycle, it takes 1 second, and it means that this is a 1 hertz frequency sine wave. And I can write it in terms of like f of t is equal to a sine omega t. So this is a normal sine wave. So when I have a sine wave, I could change it. When I say change it, I could either change its amplitude or I could change its phase. So when I mean that, what happens is, so this is a very fundamental concept. Say, for example, I'm changing the amplitude of the sine wave to twice its amplitude. What would we have? What would we expect is that we would see that the frequency is the same. What the pink curve represents the new one. So you can just see that the amplitude has increased to 2 at plus and minus. However, the cycle is completing in 1 second. So there is no much of a change to the frequency. The frequency is remaining same, and the phase is also same. They're starting and ending at the same point. So the phase is also the same. The only thing that is changing here is the frequency, is the amplitude. So that is part one. And the same wave function if I have, and if I kind of apply, if I say that I'm applying a phase shift to it, and when I say that a phase shift, I'm kind of shifting this whole wave function, and when I'm doing that, this is what happens. So over here, you could see that the amplitude is not changing. The amplitude is remaining constant, but then I have introduced a positive phase shift. So it's leading. So you can see that the current is kind of, I'm sorry, the output function, the next function is kind of leading the primary function, and this is again a phase shift, and this is how you will be able to distinguish an amplitude change and a phase change. And moving on, when you're looking at a plot like this, g of t over here would also be having a change in amplitude, and it will also be having a change in phase. So what do you think is going to happen to the amplitude? Will it become smaller or larger? Can you write in the chat box, please? Yeah, perfect. So the amplitude is going to get smaller. And similarly, do you think there will be a phase shift here, or will it have the same phase? Yes, perfect. Thank you. So you're going to see a phase shift and also a amplitude change, and this is what is happening. And in all this process, you have to remember that we are not changing the frequency. The frequency is remaining as such. Omega is not changing at all. It's just that the amplitude and phase is changing. So this is the main concept. So when I say this, I'm coming to another concept called the transfer function. Say, for example, I have a box of a transfer function, and I apply a sinusoidal waveform as a stimulus to it. And when I apply it as a stimulus to it, it goes into the transfer function. It kind of gets modulated inside it, and it comes out as a response. So when you give a stimulus, the output response would be depending on what the transfer function is. Say, for example, I'm giving x of t as a input signal to this transfer function, and this function is introducing some change in its phase and in change, and there's no much of change in the amplitude, but there's a change in phase, and this transfer function is giving me this output. So I'm able to see that this transfer function is systematically affecting my stimulus and is giving me a response. So this is one concept that I wanted to tell you. And when I move on, we can also see that we have studied all this in school, so I'm not going into how we derive all this. So we can also study a wave function in terms of a phasor. You can give a phasor, and you can also have a phase angle to it. So the you can have it in terms of complex numbers. So you can write it in terms of a wave function, and depending if it will be maximum when its amplitude is maximum, and then it will come to a lower value, and then it will come back. So this as and when this phasor is rotating along this axis, you will be able to generate a sine wave function or a cos wave function, and that's how you get so the entire sine wave function can be defined by a phase diagram, and you can see that x naught would be its phasor and phi would be its phase angle, and you could also write it in terms of its cos and sine terms. So over here I have an x of t, which can be written in terms of its time domain and also in frequency domain as this, and this is a very important equation that we'll take forward. Similarly, as I said, let there be another function called z, and if I can write z in terms of e power j is a complex number here. So if I could write it in terms of j phi, I could write it in terms of cos and sine. And over here, if I could take cos terms in the real axis and sine terms in the imaginary axis, I could get it in terms of a complex number wherein there is a real component called z prime and an imaginary component called z double prime. So z prime is going to be nothing but your mod z cos phi, and your z double prime is going to be mod z of sine phi. And the modulus of the whole of this vector can be founded by root of this z prime square plus z double prime square. And as I said, at any instant, you will always have a phase angle, and that phase angle can be denoted as the real component, the imaginary component by real component. So I hope this is okay for you. As I said earlier, I'm coming back to the transfer function. So I've introduced a wave functions to you. I have also introduced a transfer function to you. And when I say a transfer function, if I could talk to you in terms of linearly time invariant. So as I told earlier, the frequency is not changing. So when I say frequency is not changing, the time, it's a time invariant system. So if I give an x of t in a cos wave, I will get a y function. So when I say what all could be the possible x and what all could be the possible y and what all could be the transfer function, we come across these different transfer functions. The first one being impedance. So when I have impedance as a transfer function, I could give a voltage or a current, and I can get current or voltage. So it could either be impedance or admittance, the reciprocal of it. And similarly, there could be modulated photosensitive spectroscopy, wherein I could give light and I could get photocurrent. And in IMBS, I could give light intensity and I could get a photo voltage. And there are other things that I'm not quite familiar with, but I just went through. So you have electrohydrodynamics, wherein you have rotation speed and you can get current, and thermoelectric, obviously with an electrotemperature, you're able to get function basis. So as I said, this H of W can be associated with all of these components, wherein I could have this as the input signal and the output signals can follow up as and when according to the system that we are using. So the focus of our talk is obviously going to be impedance. So I have a stimulus and I'll have a response, and the impedance or admittance is going to be the transfer function. So now let's move from all those x and y's and let's talk about voltage and current and impedance as we go through. So we have a voltage here, which is V naught sine omega t. This is my voltage function that I'm going to use forever. And then I get a sine, and I get a current response, and again a sinusoidal current response. So I have I naught, which may be larger or may be smaller, and I also have a phase shift associated to it, depending on the transfer function and depending on the subject to which I'm testing. I'm depending on the testing system also. So I'm bringing back the same equation again. I hope you're able to relate to it. Now, what we have here is impedance. So I have V, I have I, and so this impedance function, this transfer function box can be given as a phasor, also as a complex number, and this impedance function can be plotted, and I'm moving from t to omega. So hereafter I'll be talking of it in terms of frequency. So this impedance at different frequencies can be given by z of t, a real component, an imaginary component, the modulus of it, and the phase angle. So this is the first representation that I can have. So when I'm giving a voltage and when I'm taking out the current, I can do it at different frequencies, and I can get an entire spectrum. So I can change from 1 meg to I can go to 100 millihertz or even below that, or I can run an entire spectrum of I can change these voltages at different frequencies and then see what's the response. So in that way, we can collect an impedance as a function of frequency. And when you're plotting, you can actually plot it in terms of Z prime and Z double prime. This is one representation. And I can also plot it in terms of log of frequency versus modulus of Z or phase angle. So these are the two basic representations that I can have. I can see that someone has raised their hands. If you would want to ask anything, you can ask now. Okay. Okay, so let's move on. So we have these two representations. So these are the two commonly used representations for the electrochemical impedance spectra. One is the Nyquist plot that we have with Z prime and Z double prime, and the other one is the Bode plot with log of frequency and modulus of Z. So each of them have their own advantages and disadvantages. Most of battery people, we use this Z prime, Z double prime, and the others who are looking at photosensitive samples and solar cells and all that could probably be using a Bode plot, wherein they could understand more of time constants and how the electron exchange happens, so on and so forth. So the advantage of Nyquist is that you will be able to clearly, at first instance, you will be able to see the kind of phenomena that is happening in it. But the point that is missing here is the frequency information. You will not know what is happening when you're looking at, unless the frequency is marked in it, you will not at a first glance be able to identify if it is at what frequency each of these components are coming. But on the other hand, Bode is having a log of frequency curve, so we will be able to easily say at what frequency what's happening and which circuit or which element is contributing to the respective impedance or a respective phase change. So this is the main outline about the impedance and the representations. Moving on, as I said, there's a transfer function over here. Say, for example, I have a voltage, a sinusoidal voltage. I am giving it through a box of an electrochemical impedance circuit, and then I'll be able to be getting the current out of it. So for first instant, let me imagine that this box is a resistor, and later I'll be imagining that this box could be a capacitor, and then later I'll tell you what would happen if this box is an inductor. So the first thing is a resistor, capacitor, and inductor. You know all these passive elements. So these are all the passive elements. So when I say you have a resistor, a resistor can be given as a voltage V by I, and capacitor Q equals CV, V equals L di by dt. All of these are the basic ways in which we represent all of these components. So first is resistor. When I have a resistor, you can see that the and I would also want to say that when I have a DC potential applied to a resistor, this resistor is going to oppose these DC signals, and we are able to see a voltage drop in it, and the output voltage is kindly going to be reduced compared to what you're giving. So when you have a DC voltage system, your load could actually give an opposition, and that opposition can be termed in terms of a resistor. But when you have an AC signal, things are quite same. So in terms of an AC signal, a resistor kind of a material will give you a resistance, and a capacitor kind of material will give you a reactance, and an inductor type of material will also give you a reactance. So a capacitor's reactance is called as a capacitive reactance, and for inductor we call it as inductive reactance. So this is how we basically, so if you have an AC signal coming in, all these reactance components will be involved, and the net output that we get will be depending on the magnitude of all these reactants, the capacitive reactance and the inductive reactance. So capacitive reactance is, so just as we have R, which is not frequency dependent, XC is actually dependent on frequency. XC is actually, the capacitive reactance is dependent on 1 by omega C. And when you have inductor, it is XL equal to omega L. I'm not going into the derivations for now, but I would just show you that this is what's happening. So, yes?
Can you explain reactance?
I would call reactance as a net opposition. If just as I have, say for example, I have a bottle of a river flowing, and if I keep an obstacle in it, you will have a hindrance to the water flow. So just as I have a hindrance to a water flow when I keep a blocking a wall or a rock, if I place a capacitor when the current is flowing, that capacitor is kind of going to cause an opposition it is not going to kind of accept your the current that's coming in or the voltage that's coming in, it's kind of going to contribute to an opposition. So that opposition is called as a reactance. All of these are resistance kind of analogs in an AC circuit, AC signal circuit.
Ma'am, you
Yes,
said in the previous slide that if we give voltage, then we get current response.
yes.
But in the plot, we are getting only
Mm.
the information in terms of frequency. So where is the current response?
I can tell you that. I can tell you that. I'll just go on and maybe we'll discuss that when at the end of the talk. Maybe I think we can discuss this again. I'll show
Okay,
you how it comes.
thank you.
Yeah. So you have a resistor, capacitor, and an inductor. As I said, you have different things. So when I have a voltage and a current response to it, you can see that the current is leading in terms of a capacitor, and the current is not lagging in terms of a inductor. So this is how you get your response. So you have a V and you have a I. For every VI associated, there is definitely going to be a Z component, and that Z component is what is being measured. So if for at a particular instance, I have V equal to, say, for example, the amplitude of P is 5 volt peak to peak, and the current is 2 volt peak to peak. I will be able to at a particular instant measure the resistance or the impedance that by a particular equation, and then get the impedance out of it. So as I said earlier, this is the circuit element. I have a stimulus and I have a response. If I give an AC signal as an input, I will again be getting an AC signal as an output at the same frequency of the input signal, provided the phase or this could change depending on the circuit element. So I hope all of you have a one sec. What is the physical significance of phase angle 45? I think we can discuss that. The linear and capacitor both phase change and amplitude. Okay. Uh, okay. The capacitor, what happens is you can, depending on what is happening, you can also have a current change and current change, and that current change can also be associated with the phase angle. If you could look at the impedance derivations, like V equal to, if you assume V is equal to V naught sine omega t, and then you put it in this equation, you can write current Q in terms of dq, in Q in terms of current, and when you integrate the response, you will be getting a cosine function, and that when you're relating, you will be getting the amplitude of current, and that's how you're plotting your voltage and current. So your current is not going to be the current's amplitude is not going to be the same as your voltage amplitude. There's definitely going to be a change in that, and provided just as there's a lag of a 90-degree, you can find that because you're integrating it, and you'll be getting a cos term associated to it, and that's why there's a phase change also to it. Moving on, so you have a stimulus, you have a response. So I would want you all, I hope I've made it clear that if I have a voltage and if I have a current response, I would be able to measure the impedance at a particular instant, and that impedance can be plotted in terms of a Nyquist and a Bode plot. So I could have a resistor, a capacitor, or an inductor. So the first task would be, I hope all of you have a paper and pen with you. I will be giving different circuit elements, and we are going to draw the Nyquist plots and Bode plots for it. And I would want you all to give me the values for it. So before I move on, I would want to tell you that for every element that I'm going to tell, this is going to be their values. So the resistor is going to be a 1K resistor. You can write it down somewhere. The capacitor is going to be a 1 microfarad capacitor, and an inductor is going to be a 1 microhenry inductor. So the frequency range in which we are going to, so at every, the frequency range in which we are going to give a voltage would be 100 millihertz to 1000 kilohertz. So this is what is going to be our input signal data. And as I said, these are the formulas that you can refer to when you're doing your calculations. So we'll move ahead. When we are doing this plot, I would want you to know that I will be plotting my frequency in terms of log. So when I'm moving from 100 millihertz to 100 kilohertz, log of 100 millihertz is equal to, can someone say what's log of minus 100 millihertz? Log of 0.1? Minus 1, yeah, perfect. What is log of 100K, like log of 10 power 5? 5. Perfect. Yeah. So you will actually, when you're plotting, when we are going to look at the results, we will have this axis ranging from -1 to 5, and we are not going to plot all of these values. So if you would like to imagine, I'd say, so now you have a resistor. Resistor is going to be a transfer box. You have a wave function with any voltage amplitude. Don't worry about the amplitude. And you're giving it at different frequencies. You're only going to change the omega of it, and you're going to look at the current response and see what's going to happen. So since we already know that a resistor has a what is going to be the impedance is that Z is going to be root of R square plus XL minus XC whole square. So when you remove, we don't have an XL component, we don't have an XC component. The root of R square is only going to be R. So Z can only be represented as R1, and this is going to be your resistor value. So say for example, I change it from different frequencies. Let's take 100 millihertz first. If I'm changing irrespective of it being 100 millihertz or irrespective of it being 100 kilohertz, R is not going to change, and R1's value is going to be there for the component. So when I look at it, the real part of it is going to be R1 and the imaginary part of it is going to be 0. So how do you think this plot is going to look like? At any instant, at any frequency, Z is going to be equal to R1. So
Straight line.
a straight line. Okay. Why do you say it would be a straight? Okay, we'll see. Anybody else?
Point in the x-axis.
A point in the x-axis. Yeah, I'll tell you why it's not a straight line. It's only a point. Say for example, this is your outline. I'll just say it. Few of you who know might find it a little slow, but I just want to discuss this first. So this is going to be your impedance function. Say for example, I first measure it at 100 millihertz. Okay, at 100 millihertz, there's no frequency component. So Z at 100 millihertz, Z at 100 millihertz is also going to be R1. Z at 100 is also going to be R1. Z at 1000 kilohertz is also going to be R1. So irrespective of what the frequency is, Z is always going to be R1, and there is no imaginary component associated to it. And therefore, what you're going to get is just a dot in the real axis, and that real axis R will correspond to the resistance that is here, and that is going to be a point. And can you say what would be the value of that point?
Hello.
Yes. Yeah, perfect. Yeah, the point is going to be 1000. That's it. Perfect. So the first step is clear. So you're going to get a point, and that point is going to be at 1000. So if you're having a 5K resistor, it's going to be at Z prime equal to 5K. If you're having a 100 ohm resistor, your Z prime is going to be at 100. Irrespective of the frequency, no matter what you point, at every frequency, it's going to be a point over a point over a point, and that's going to fall at the same point on the real axis, and that value is going to correspond to your resistor's value. Moving on, let's now calculate mod Z at different frequencies. Again, when we look at mod Z is equal to root of the real and the imaginary component. And here again, when you look at it, it's Z prime square. So Z prime is square and root, so it's going to be Z prime only. So eventually, what is going to be a mod Z is that your mod Z is again going to be a straight line. So at log of f equal to -1, it's going to be R1. At log of f equal to 0, 1, it's going to R1, 2, 3, and 5. At the entire frequency range, your modulus of Z is not going to change, and that's eventually going to be a straight line. So this is 1. And again, when you're looking at the tan inverse of tan inverse of this, so that's going to give you the phase angle. So it's Z double prime by Z prime, and when you look at it, this is what you're going to get. So your Nyquist plot is going to be just a point, as all of you said, most of you said, it's going to be at the resistor value. And then your phase, the mod Z is going to be at this value. So it's in log scale. So it's going to be written as log of 1000, which is equal to 3. So irrespective of your frequency, it's going to be the same. And when you look at the phase angle, it's tan inverse of Z double prime by Z prime. So that Z double prime is 0, as I said, there is no imaginary component associated to it. So it's going to be tan inverse of 0, which is 0. And you could see that there is a green line at the phase angle of 0 over here. So this is the Nyquist and Bode plot of a resistor alone. So I give in a sine wave function of a particular voltage and I get a transfer function response, and the transfer function is going to be a resistor here, and this is how the output response is going to be. So I have a voltage, I have a current. Depending on the voltage and current response, we'll be getting the same information, and we have deconvoluted it in terms of impedance, and this is going to be your output. Is it okay for you? If you're okay with it, can you give me a thumbs up? Okay. Okay, good. That's nice. Thank you. So let's move on to another similar equivalent circuit that is going to be a capacitor. So now here again, I'm not going. So you are now kind of familiar that it's going to have a frequency from -1 to 5, and then the capacitor's value is going to be 1 microfarad, and you will have to do a little bit of calculations now. So let's start with a capacitor's equations. For Z, for capacitor alone, it is going to be Z equal to 0 plus 1 by j omega c. This 1 by j omega c is what we saw already. There's not going to be any real component because the only way a capacitor is related to an impedance is 1 by j omega c with no real component to it. So this is going to be the system of study. So when I say it's going to be omega and c, you will have to, when you're doing your calculation, you will have to write omega in terms of, you'll have to write frequency in terms of omega. So at any instance, if I'm giving you a frequency, you will have to multiply it by 2 into 3.5. So any frequency that I'm saying, you will have to multiply it by a factor of 6.28 and then do your calculation. And your capacitor is going to be of 1 microfarad. So let's look at it now. You have a capacitor, 1 microfarad, and let's look at two different frequencies. Let's start with 100 millihertz first, and let's go to 1000 kilowatts, and in between we'll see what's happening. So at 100 millihertz, I want you all to calculate Z. So Z is equal to 0 plus 1 by j omega and c. Omega is going to be 100 milli, like 0.1 into 6.28 and into your C, which is going to be 10 power 6. If you're doing that, what is the value that you're getting? Yeah, I'll come back to the explanation later. Let's finish this and I'll just tell you how we are getting the equations. So Z is 0. Z is equal to 0 plus 1 by omega c. When omega is equal to 0.1, what's happening? And when omega is equal to 10 power 6, what's happening? Yeah, minus 1.5. Perfect. That's right. Very good. So you're getting minus 1.59 here for your 0.1 millihertz. And what is happening if it's 10 power 6? So when it's minus 1.59 j, it's going to be a point. Yeah, so it's minus 1.59 for one. And what is going to be the other value? Okay. Can somebody calculate it for 1000? Like 10 power 6? 10 power 5? It's going to be this actually. So it's 1 by j omega c. So when your omega is high, when your frequency is high, your Z value is going to be low. So it's going to be on the top side, like close to 1000. If somebody's done it right, it will be close to 15926. And if your Z value is low, it will be close to 1.59. And so this is what you will be getting for your capacitor. And similarly, when you're plotting your when you're plotting your log of mod z and log of frequency, this is what is going to be your response. You can again calculate it. So you will be knowing that it is going to be mod z is going to be root of z prime square plus z double prime square. So this is not going to be there. It's only going to be 1 by omega c. And if you are squaring and plotting it, if you could do the calculations, you will be getting a value of like close to 6.2 over here. And over here, you will be getting a value close to 0.2. So this is how you plot your mod z value. And your phase angle also, if you're plotting, it's going to be tan inverse of z double prime by z. So z double prime is 1 by omega c, and z prime is 0. Z prime is 0. So tan inverse of the value will be giving you a 90 degree, 89 point something. So you are getting a phase angle over here. You can do these calculations if time permits. So now it's like we are already running late, so I'll just move further. So it's j equal to 0 plus 1 by j omega c. I can write it as minus j into 1 by omega c. And when I'm doing so, this is going to be here in this quadrant. Somebody asked the same doubt yesterday. But when I'm writing it in terms of minus, I'll be able to change the quadrant and I can present it in the top axis. So I'm rather than writing the representation here, I'm putting minus of the imaginary here and the real component here. And all the plot that we are getting is going to come in this quadrant of your impedance plot for your capacitor. And moving on to an inductor, the same is going to happen for inductor. So for an inductor, you would have Z is equal to 0 plus j omega L, and there's a frequency dependent direct contribution. If you could do the calculations in a similar way, if you could have time, you can do all these calculations and you can see that it is j omega L. So as you increase, Z is equal to, so with higher frequencies, your Z value is going to increase, and with lower frequencies, your Z value is going to decrease. So you will be getting a straight line in the negative value, and your real component is 0. So you're not going to get anything here in the real part. And similarly, you have a mod Z equal to root of Z prime square here. So for calculating mod Z, it will be kind of the ulta. The values that you're going to get is going to be reversed actually. So at 100 kilohertz, you have 10 power 5 into 10 power minus 6. And when you're doing your calculations, you'll be having a value close to 0.2 here and close to 83 or something here. So that's how your whole plot functions. And phi is again equal to tan inverse, and it becomes minus 90 when you're doing the calculations here. So it's j my omega c, and that's how it comes. So when I'm doing this, you're now able to know what's happening to a capacitor, what's happening to a resistor, and what's happening to a inductor. Moving on, if I have a resistor and capacitor in series, this is what happens. You have a resistor and a capacitor. So you have two terms. You have a real term with the resistor and an imaginary term with the capacitor. So now we are going to get both these contributions. So you have R1 plus 1 by j is minus j, and 1 by omega c1. So this is going to be the impedance value that you are going to get. And if you calculate, if you could find time and calculate, we are already close to 8, so I'm just ignoring this. So if you could calculate at lower values, at lower values and higher values, you'll be getting a straight line, but the straight line is going to be biased. So earlier it was 0 minus this factor. Now you have another R1 factor. So it's again going to be a straight line. But the point is that it's going to start at 1 and it's going to go. So at higher frequency, it's going to be closer to the, it's going to be a low value, and the impedance is going to increase when you decrease your frequency and go close to 0. So this is your resistor series RC combination. And similarly, you will have a phase diagram. So over here, if you look at it, it's like you have two components. You have a drop here and you'll have a drop here. So the net result is what you're going to see, and you will have a S-shaped curve, and this dip over here and this dip over here will denote, and we'll be able to find out the time constant from these values. So again, if you could do the calculations, you could substitute R1, you substitute C1 at a lower frequency, and at a higher frequency, if you could get, you will again get the same value close to 89.96 and then close to 2.77, and this is what is going to look like. Moving on, this is again
Excuse me, ma'am. Can
yes.
you repeat that?
I can actually start and do the full derivation. Say, for example, I have a resistor and a capacitor in series. So my value is
Ma'am, actually, body plot I want to know. that? What?
Bode plot. Okay. For
Okay,
a
okay, last one.
for a
For
capacitor
RC
or
circuit, RC circuit, RC
for
circuit.
for an RC circuit. Okay, this is here. So now this is what you have. When you look at the Bode plot, shall we plot it for impedance of a phase angle?
Yes, ma'am. Actually, you talked about that frequencies now. The or in the two questions we have right?
Yes, yes.
Nearly at the low frequency at 1.5 something.
Yes, yes, yes.
So what you said, I didn't hear that one. That's right.
It's like when you're plotting these extreme values, say for example you have a phase angle over here, so when you start with it here, for the real components, say for example you're starting with r1 minus j1 by omega c. When you're having frequencies close to 100 millihertz, like 0.1 frequency, you're going to get a value close to, I've already calculated, I can show you that like this plot. Say for example it's tan inverse d by a, so it's going to be your b is going to be 1 by omega c, and your a is going to be r, so it's going to be 1 by omega c r. So this is going to be your tan inverse value. So when I put it at a lower frequency and at a higher frequency, for a smaller hertz, say for example at 0.1 millihertz, my value is going to be 89.96. That's where this value is coming. And at the other value, it's going to be 2.7. So this is the extremes. Now, when you look at the intermediate, as you asked, you can see that it's 1 by omega CR. So when you equate it to 1, you can find out the time constant. And with the time constant, you will be able to see what value the omega is going to be. Omega is going to be equal to RC. So whatever RC is associated to omega, with that omega, if you could calculate tau, that value is what is going to come here.
Okay, thank you.
I hope I'm clear with that. So you have an RC component associated with it. The RC is going to come at a particular frequency. This bend is happening. So whatever frequency the bend is happening, that's the response time, and that's why you're going to get your time.
So that is a knee frequency or a knee frequency, right?
That is a knee frequency. Yeah,
Yes,
that's
okay,
a
okay. That is the point. So in here it is like a low frequency near to 1.5 we can consider as a knee frequency.
Yeah, yes.
Okay.
Okay. So now this is RC in circuit. Now when we move to R and C in parallel, it's again J equal to, again if you are having, you have two components. So this is going to be your circuit. Your circuit is going to be quite a little complex to look at. So it's going to be, these are in parallel. So you're going to add, the net of impedance is going to be 1 by Z total equal to 1 by Z1 plus 1 by Z2. And in that case, if you could look at Z total, it's equal to 1 over 1 by R1 plus 1 J omega C1. This was a reciprocal, it went up. And when you solve this, you have a J term associated here. When you rationalize it, you have two components. So these two components are again quite complex to solve, but again I have done it. If you are able to put the numbers in it, you will be able to get the minimum maximum values. And basically what happens is, if you could look at it in another way, in a normal term, if you're applying a current on a voltage, or if you're applying a current here, this is going to split to two components. Okay, so which part of it is going to go to the upper region and which part of it is going to go to the resistor depends on the frequency. So it's actually basically acting like a filter. So at very low frequencies, your capacitor is not going to work. So all the current that is going to go through R1, and eventually the net impedance is going to be only contributed by R1, and that R1 is coming over here. So this is point number one. And the other way around, if you are able to have your capacitor at higher frequencies, your capacitor is also going to contribute. So all of what is going through your capacitor will be at its maximum, and all of what is going through will be going through the capacitor, and this resistive component is not going to play a role. So you will end up having a semicircle, and eventually there will be a point wherein current flowing through C1 and R1 are both same, and that will happen at a particular frequency, and that is where you get this maxima. So this is where you get the maxima and equal current going from through the capacitor and resistor, and this can be associated with omega, and from this omega again you will be able to get the time constant. Again, with so much of complications, it's difficult to find out here. Rather, if you're generating the Bode and the Nyquist plot, the same can be done here, and you'll be able to find out the rate constant from the Bode plot. So this is for a resistor and a capacitor in parallel. So again, if I'm having the same thing, if I have an R0 and if I'm having a C1 and R1 in again in series, what I'm doing is I'm just giving a bias resistance again. So the same is going to happen, except that you're going to get an R1 here, and this R1 is R0 here, and this R0 is going to be the initial solution resistance, or the initial resistance that we have here, and that's going to start from 1000 kilo, and the same is going to continue. So net effectively at this point, at a very high, at a very low frequency, your current is going to flow through R0 and R1, and your Z is going to be just R0 plus R1. And over here, when you see your at the maximum frequency, your current is going to flow through R0 and C1, and the net real component is going to be R0 and C1. So this we have already seen at very low frequencies, it's not going to be effectively R0, and that will be a point here. And the rest follows in the intermediate point. And again, from here, you will be able to find out the rate constant. So this is for one common and a very popular circuit. And over here also from the Bode, you will be able to find that there's a change in phase angle, and the phase angle is maximum at a particular point. And again, you will be able to find out the rate constants here. You have two rate constants here, tau 1 and tau 2, and you will be able to find out the two knee voltages in both the circuits. And moving on one step further, if you have two RC elements, it's just an addition to what we have. Again, it's the same kind of a description what I've showed you. It's just that you're adding the components, and in mathematically, when I'm writing, this is going to be the Z term that I'm going to generate. So it's going to be a bit more of a complex term. And you can always understand that for every RC combination, you're going to get a semicircle. Yes, yes.
Please use that pointer. Is
Oh,
very
okay.
stylish.
Yeah. So you're able to see, right? Yeah. So you have an R0. You have a. I think I can.
First option.
Yeah, I know. I just thought I could increase its size. I don't think I can. Yeah, okay. So you have an R0, you have C1 and R1, another C2 and R2. So wherever you're going to have an R and C in parallel, you're going to get a semicircle, and that's the basic idea. And wherever you're having an R0, you're going to get a shift in the impedance plot. So the first thing is you have an R0 and a C1 and R1 here, and a C2 and R2 here. So you start with your R1, R0, and the first semicircle is going to be associated to the first part, and the second semicircle is going to be associated to the R0 plus R1 plus R2. So this way, you're able to identify a complex circuit, and you are able to look at this plot, and you are able to get back to the equivalence. So now that we are generating from the equivalent circuit, you are generating these semicircles. But rather, if you are able to see two semicircles, you must obviously know that it's going to be of an RC combination. And when you know that it's an RC combination, you will be able to know what these individual values are corresponding to, and you can follow up and reduce the equations for them. I hope that is also clear. So this is how it's going to work. So we are not, when we are doing our electrochemistry, we are not going to know what the circuit is. Rather, we are only going to know what the plot is. And from this plot, we are going to see, okay, this could be the resistor, this could be the capacitor, this could probably be the equation and the model which we can fit the Nyquist. That's how we are going to interpret the whole process. So when we are doing a measurement, we have different electrochemical test systems. So this is for catalysis. Most of you will know that this is HER, OER happening. And for batteries, you have a redox couple. You have a charge transfer. This is, I probably believe, an LiFePO for cell. You have different couples involved in it. And when you're looking at these phenomena, you again have a potential and a current response. And you can note that at every instant, this is not same. It is not linear either. At every potential, they're having a different response nature, and we must be able to know what is happening at each of these stages. So this is the main concept. So you have an electrochemical test system. You apply a potential, you can get a current response. You apply a pulse current, you can get some time voltage time response. And similarly, when you're doing an electrochemical impedance measurement system, you are getting a Nyquist or a Bode plot of the same electrochemical system. So we are quite familiar with these. These are our results. The current and time are the results that we have. These are the stimulus that we are applying. And with this, we are able to see what is the, if it's a battery, I'd say how good the capacity is. If it's the catalysis material, I would say how good the over potential is. Similarly, for a electrochemical test system, when I'm applying an impedance EIS run, I would be able to get the Nyquist and Bode plot. And with this Nyquist and Bode plot, as I have shown you earlier, if you are able to sit and calculate, you will be able to get a combination of circuits. So it's the same electrochemical test system. I get a Nyquist plot, and I'm able to represent it by a combination of a circuit elements. And by this whole process, what we are able to do is we are able to equate this entire electrochemical system to a combination of circuit elements. So this is what electrochemical impedance spectroscopy is all about. So depending on the plot you have, you fit it with different components, passive components and some active components. And with that, you can kind of relate what your electrochemical test system is at a particular voltage. So mostly we do it at our OCV. I will tell you a few examples later. So as I said, you have a potential, you have a current response, and mostly we will have to apply a AC signal to it. So when I say if this is, say for example, when I say this is the voltage current response, if I want to know what's happening at say close to 1.7 volt, I must know what's happening at this potential. So at this potential, if I want to study, I will be applying a sine wave perturbation of a voltage perturbation, and I'll be rescuing. Say for example, I want to measure it at 0 volt, I would just apply a sinusoidal potential with 0 as the base. Otherwise, I could shift it, and at a particular voltage at 1.7, I can measure, or at 0.5, I can measure. So at different frequencies, I can go and I can apply a small voltage perturbation. And when I say a small voltage perturbation, say for example, if I would want to, sorry. Okay, so let's leave. So if I want to study the system at 1.5 volt, and imagine me giving a voltage perturbation of amplitude close to 1 volt, what would happen is the sine wave is going to be superimposed, and its superimposed sine wave will have a very large peak to peak difference. And when I say a very large peak to peak difference, it is actually like I'm not studying at this range, but rather I'm going to this potential and studying. So I must always make sure that I select a region, a small region, and that region is linear, and only in that linear region will I have to get an impedance measurement done. If I'm going beyond the linear region, and if I'm applying a sine amplitude much larger, the information that I'm going to get is not going to reflect on the system or the potential, but it is going to be some other artifacts coming into picture. So this is, for example, a small sine wave signal. In mathematical terms, this is also a way in which I could reflect. So a diode characteristic, if you could see, this is the voltage current response. And say, for example, I would want to understand what's happening here. So as I said earlier, V is the voltage, and this BSS is the point where I want to study. So I am applying a small potential, a delta perturbation potential, and that perturbation potential is equal to V e power I omega t. So when I'm applying that perturbation potential, I'm obviously going to get a current. So that current, I would call it as delta I, and that delta I is going to be a function of BSS and delta V potential that I've applied. And if I could expand this in terms of Taylor series, I will get f of VSS and then differential of f of VSS and del V. So this is the entire expression that I'm going to get. If you can look at it carefully, ISS and VSS are obviously going to give us the resistance impedance value. And what you see is the delta I. So the delta I response that I've got here is actually equivalent to f prime of VSS into delta V. If the delta V is small, I can ignore all the higher order terms, and the only voltage that I would get is equal to f is going to only be related to delta V. So del I is directly proportional to the small perturbation I'm giving, and I could say del I is equal to I e power I omega t, and f prime of Vs is going to be as such, and this is going to be the V equal to perturbation signal of V e power I omega t. And when I'm dividing it, and if I want to know what this transfer function is, so this again is a transfer function. If I want to know what the transfer function is, it's actually the admittance is going to be I by I over V, and it's going to be a derivative of VSS, and that's actually going to be 1 by R. So this entire region, if I assume is a linear function, I can ignore the higher order terms. Provided this perturbation is small, I would be able to get that the admittance value is equal to 1 by R. So we are now at this particular voltage being able to identify equivalent circuit element, and we have linearized this non-linear response to a resistor-like circuit. So this is why we need a small perturbation. So if anyone is going to ask us why we are not going to a higher perturbation and restricting to 5 millivolt or 10 millivolt, this is going to be the reason. We don't want artifacts corresponding to higher order voltage perturbations, and we are limiting to a smaller value to assume and go towards a linearity. So this is the real circuit here. So I said that there is a diode here. I naught is equal to 1 microampere. And I said that there is a resistor, and I find out that the value at 0.2 is 10.7. So when I'm going by a small voltage change, I can actually calculate that value. Say, for example, del V is 1 millivolt. Del I is going to be Y times del V. Admittance here is going to be 1 by R, and it's 1 by 10.7. If I see that del V is going to be 93.5 microampere, and when I do this, I'm able to get a value of 93.5, but the actual I change is 95.4 microampere by a proper diode characteristic curve. So 94.5 is what I should get, 93.5 is what I get. We're able to kind of get a closer value provided our delta V is close to 1 millivolt. Rather, if I'm going on a very higher step, like say, for example, I'm going from 0.2 to 0.3 millivolt. This is a very high voltage change, like close to 100 millivolt change, and J does not step. The value that we get here when we calculate is 4.9 milliampere, and that is not going to be the actuals. So the actuals that we get is going to be different from the real system. So provided this is another explanation, unlike just as we could get it from the Taylor expansion, even when we apply the same experimentally to a circuit, this is what we get. And for smaller perturbations, it's linearized, and for higher perturbations, it's not going to be linearized. So always for an electrochemical impedance measurement, we ensure that our voltage is going to be very small, and that's how our perturbation has to affect our system in real. So moving on, as I told you earlier, we have an say, for example, this is one example wherein you have an electrode and then you have some solvated ions. This I can actually represent in terms of electrical circuit elements. Say, for example, I can associate this with a double layer capacitor. I have an electrode and an electrolyte. I have ions accumulating, and then I can have an electrochemical double layer. I can also have a charge transfer resistance. Say, for example, for a reaction to happen, for an electron to transfer, there has to be a charge transfer resistance across the boundaries. That is again given over here. And also, we will have an electrolyte resistance. So the ions have to move through the electrolyte. So there will be an electrolyte resistance to it. So these are the different resistance components that you could see in a very simple system wherein you dip an electrode inside an electrolyte. So if you want to generalize this in terms of an equivalent circuit, this is how it's going to look like, and this is the Randall's circuit. And provided that they've already solved this circuit, so you must be knowing how the circuit is going to look like. So how will the circuit look like? You have an R and a R and a C in parallel combination. How do you think this is going to look like? Is it going to be a straight line or a semicircle? Yeah, that's good. So it's going to be a semicircle, and semicircle that has a starting point close to this solution resistance. Yeah, good. Thank you. So this is how we are going to model systems. And when we come into a little bit of more of concept-oriented ways, we also have different other elements. Say, for example, we have a resistor, capacitor, and inductor. These are all passive components. There are also a few other components that are time dependent, and they have a distributed rate constants, and that they are I will explain what they are here. I'm not going to explain the theory and the derivations and all that. I'll just tell you what they are and what they are meant for. Say, for example, a Faraday reaction has to happen. So you have an electrode-electrolyte interface. You have a species that is going to be redox active, and that's going to be converted from one state to the other. It could either be oxidized or it could either be reduced, and it will have to go through the electrode. So this is going to be a simple system. And when we look at that, when you have a redox couple associated, you will have two different mechanisms. One is there could be a charge transfer resistance, and then other is there could be an impedance. So I'll tell you what this Warburg impedance is. This is an element that is associated with the mass transfer. So your ions are moving. Similarly, your reactive species should also be able to move through the bulk of the electrode. So mass transfer through the bulk of the electrode is represented by a Warburg impedance. So this, say for example, I have this is going to be the initial case. So I have an uncompensated electrolyte resistance. I have a double layer capacitance. And then there was earlier a charge transfer resistance. Now, since mass transfer is also involved, I call this Faradaic impedance. And this Faradaic impedance will be given as charge transfer and Warburg. And this is what we get. So you have ZF. This ZF can be deconvoluted as two terms. One is charge transfer and the other is Warburg. So charge transfer is mainly for your redox electron transfer. Warburg is mainly for mass transfer. So this ZF can be deconvoluted into two. One is the RCT and the other one is Warburg. This Warburg element has its own way of representation. So just as I said, R is going to be a dot, a capacitor is going to be a straight line, and an inductor is going to be a negative straight line. This Warburg impedance is going to be a straight line of a slope, and it's going to be an angle of 40. I have an angle of 45 degree with the real axis. So again, it's a very similar explanation that we had earlier. You have current coming in. So that current is going to split into two terms. One is for the charge double layer, and one is for the Faraday. And when it is coming for the Faraday, it could work in two ways. So at lower frequencies, as I said earlier, it's not going to have a capacitive contribution, and it is only going to flow through this circuit element, which is going to be the RU, RCT, and ZW. This is what you will be getting when you're looking at a lower frequencies. And at higher frequencies, if you want to go through, you're going to get a value close to a semicircle. So if you're plotting an impedance, when you're starting at higher frequency, and when you're going when you're starting at higher frequency, when you're going to lower frequency, this high frequency component will come first. So you have a RU. You know this, it's going to, as many of you said, it's going to be a high frequency component. So you go from RU, and then you get a semicircle, and you end it at RU plus RCT. So this is going to be the point here at the z-axis. And again, you will have a maximum point. And from that maximum point, you can calculate the rate constant, and it's going to be a semicircle. So this is how it is going to be at higher frequencies. And moving on to larger frequencies, this capacitive contribution is going to be very negligible. And what you're going to get is close to this equivalent circuit, and that's going to be a slope at 45 degree. So you are going to actually compress. So when you're going from a high frequency, this is going to happen, and at low frequencies, this is going to happen. So you're getting two different phenomena, and your circuit is going to be looking like something like this. So I hope I'm clear. I hope I've conveyed. So you can look at the semicircle here, and you can look at this 45 degree angle here. You get two of these. You have RU, CDL, RCT, ZW, each of these components now being able to be, so we are able to kind of deconvolute this whole plot into what has happened. We are able to identify what region is associated to what. So high frequency, we are able to associate with kinetic control, and the low frequency range, we are able to associate it with mass transfer. And that is how this works. So you can do a little bit of theory, find out what this value is. I'm not going in detail about it because only those of you who would require it can go back and read on it, or maybe I will give a detail on the data interpretation in my session that is coming the day after tomorrow. So this is what is going to look like. So when you have a cell like this, And when you've assembled a cell with this kind of an equivalent circuit, which is a double layer, say for example, I'm assembling a cell and you're assembling a cell. My Ru is close to 5 ohms and your Ru is close to 0.1 milliohm. Obviously, we could say that yours is a better material, your electrolyte is better, and that's giving a better conductivity, and therefore, so you can judge what's happening. Say for example, RCT, my Ru plus RCT is coming around 40, 50, and yours is turning out to come close to 20 or 10 ohms. Again, we will be able to say that you have prepared your electrodes before better, your coating is better, and therefore your cell is going to perform obviously better. So even before running our cells, if you have a cell and if I have a cell, if we plot a Nyquist plot and look at the expressions and the values, we would obviously be able to correlate it with how good your experimental results are going to be. So that is the basic idea of the entire fitting and analysis parameters. So again, when most of us are doing our experiments, I heard that equally there are many people who have done your experiments. We are not going to get such beautiful semicircles. So we will have semicircles that are suppressed. Some you would feel like it's looking like a mountain kind of a profile. You're going to get different profiles. So one main parameter, just as a Warburg element, is another parameter, and that is called as the constant phase element. A constant phase element is something that is not an ideal capacitor kind of that, and that's because for an ideal capacitor you'll have a very clean surface, the roughness is not going to be there, but in a real system you'll have electrode roughness, you'll have porosity associated with it, all those factors come into picture. And rather what happens with the constant phase element is that for a capacitor, if you just look at, if you're running a capacitor, you're not going to get an Ru, and when you're running an instrument for a supercapacitor application, you're not going to get a straight line, you will be getting a slightly slanted line, and that is because it is not going to be fit with a capacitor but a constant phase element, and you attribute it to the roughness, the porosity, the thickness, all those parameters. So when in series, your capacitive behavior is not going to be there, you're going to have a deviation. And when it comes to RC parallel combination, it's not going to be a semicircle here, but it's actually going to be a semicircle that is tilted, and the tilt angle is given by theta. So this tilt angle is what tells you how suppressed your semicircle is going to be, and that is going to be mathematically associated with the constant phase element parameter. So anytime we are going to fit, if you are getting a semicircle, if you are getting an ideal semicircle, when you are fitting, use a capacitor's element for fitting. And if you are getting a suppressed semicircle, you can better use a constant phase element, and that is going to be more or less realistic. So I am now coming into a few real-time systems. So you have porous electrodes associated with the materials. And when you have a porous electrode, this is how your circuit is going to be. So you have R and C's and R and C's parallel. So when you have a porous electrode wall, you call this a transmission line. A transmission line is a combination of R and C's arranged in this way. And because of the distribution of within the bulk, your electrolyte has to go and your ion migration has to take place. Ions have to be accessed. So you will have a distributed RC, distributed time constant, and you will have this as your equivalent circuit. And similarly, if your porous electrode is also redox active, similar to what you have here, you will, rather than having just a capacitor, you will have a capacitor and a Faradaic element associated to it. And this is how your porous electrode will look like. So this is another kind of fitting that I wanted to discuss with you. And another example is a biosensor. So I am not quite familiar with this, but when I went through the review paper, I was able to see. So you have a material and maybe an antibody coming to a substrate, or getting attached to an analyte or so on. So when you look at it, you can see that there are species coming and getting absorbed to your substrate. And if you would want to find that out, you could do that through an electrochemical impedance spectroscopy. Say, for example, A is your pristine material, and then there are two species. One is a bacterial species, and another is a E. coli species, and another is a streptococci species. So when you see that this particular substrate can favorably absorb your streptococci and not absorb your E. coli. In that case, what will happen is your E. coli is going to be the same, because since your E. coli is not getting absorbed to your substrate, it's not going to change, and the value of the electrode-electrolyte interface is going to remain as the pristine one. Rather, if you're going to have a species that is going to come and get absorbed to your substrate, you will have another semicircle associated to it, and that will quite increase the charge transfer resistance. Why is it going to do so? It's because you have a double layer kind of a substrate here, and that is going to hinder your charge transfer, and therefore you're going to get a bigger semicircle associated, and that semicircle can be associated to how much of deposition or absorption has taken place in the biosensor aspect. So that is one example. And moving on to batteries. So again, most of you know that there are anodes and cathodes and electrolytes, and there is an SCA formation happening, then there is a separator in between. So this is what is, yes, I am explaining for electrolytes. So this is what's happening. So you have a copper foil, you have an anode. Now this anode is actually a graphite anode. This could be an LCO, typical battery kind of material here. You have different interfaces. So for now, let's kind of try to relate it to what could happen. So a copper could have a bulk resistance. A metal wire could act as a resistor here, depending on the resistance it has. So you have it here. And then you have a graphite anode. So that you can associate it to a kind of a Randall's material. And then you have an SCA that is again associated to an RC double layer material. You have an electrolyte that is just going to allow or block a lithium depending on its viscosity and other parameters. A separator may not be involved, but for now we are having that also included. And an electrolyte again with an electrolyte and the thin film cathode electrolyte SCA, you can call it CEI. You have another film here and again a cathode here and an aluminum foil here. So when you are to study a system like this is how you are going to deconvolute it based on the understanding that we have. But what we actually get is a combination of all these elements. So similar materials with similar time constants kind of club together, and what we get are circuits like this. So you have two semicircles. When you look at this profile, I think if for now you must be able to see that there is a 45-degree here that could be associated to mass transfer and diffusion, and then you can possibly deconvolute it to two circles, and we don't call it semicircles, we call it suppressed semicircles. They're not identical. So since they're suppressed semicircles, we can associate it here. They've given it as a capacitor, but I think you can use a constant phase element to fit it. It will be much better. So you know that this is what is happening. So majority you have bulk electrolyte resistance, all of probably coming from this electrolyte contribution, because your metal current collectors are not going to contribute much. And then whichever is your SCA component, that is going to give you an SCA resistance. And then you have your charge transfer Faraday component associated to it. So this is how you are going to get your Nyquist plot plotted. Okay, yeah, I'll do that again. Yes. I'll revise it at the end. After this session is over, we'll go back to our simple circuits. So this is how it happens. You have RSA and RCT. So you have two semicircles and you associate it, and this is how we fit our normal equivalent circuits. Moving on, this is another example of a solid electrolyte. We have solid electrolyte systems. The system is quite complex. So in this work, they have a solid electrolyte, and they also have added some ionic liquid on the interface, and then they have assembled a symmetric cell. So you have a lithium, a solid electrolyte, and an ionic liquid electrolyte, and then a lithium. So you can again deconvolute it into 1, 2, 3, 4, and 5 different phenomena. Over here, you call it the bulk grain. So when you have a solid electrolyte, it's actually made of crystals packed together, densely packed. So you have a bulk grain here. So these for a lithium ion to move through it, you will have a bulk grain resistance here, and then there could be some grain boundary resistance. For the lithium to move from here to here, it has to cross this grain boundary. So the grain boundary resistance will be there, and then from this solid electrolyte to the liquid electrolyte, if ionic liquid, it has to go. Again, there will be a double layer kind of a process here. This is again an SCA, double layer with an electrolyte and electrode, and then there will also be an ECR, a charge transfer kind of associated phenomena. So this is what it looks like. And when you want to know what's happening, one more question that all of you could ask is, we have a semicircle like this. So we are going to kind of club all these phenomena and associate them to different semicircles. The first thing you could all ask me is, how do I know which semicircle is corresponding to which phenomena? that is where we'll have to go back to our theory and look at what are the rate constants and what is the response time associated with each of these frequencies. So probably mostly bulk grain boundaries, bulk transportations happen at close to 7 megahertz to 7 or 6 or 5 megahertz. So I can associate this to this. I can similarly associate these with, I can also do is I can prepare a control experiment. So I know that this bulk grain is coming here, and I do not know what is going to happen with these other semicircles. Over here, what I do is I will again control experiment. I will prepare a cell with lithium, solid electrolyte, and lithium, and then run an impedance. And when I do that, I will notice that there is this component alone and all these three semicircles are not there. When I know that, I will definitely be able to find out that the second semicircle is again coming from the grain boundary, and that's how I associate it with the grain boundary resistance. Similarly, all these electrolytes can be controlled in another system, and their values and their frequency ranges associated with their omega max can be compared, and we'll be able to see how the entire spectrum is evolving, and based on the different phenomena, we'll be able to correlate what's happening. So this is the basic idea, and I would say if you ask me how a sensor works, I might not be able to know. So with impedance spectroscopy, it's based more into going back to literatures and looking at equivalent systems and seeing how they have interpreted it and going in the same line. So for a battery chemist like me, if I look at an impedance plot, I'll be able to associate it easily to different phenomena occurring in a battery. And that's because we have been going through this process for a long time, and it's easy for us to associate different plots and different regions to different elements. And within 10 or 15 minutes, we'll be able to plot an equivalent circuit and go ahead with explaining them also. So all of you, I would suggest that impedance is a very nice tool. Even if you are assembling a setup, if you have an EIS option, I would suggest that you could run an EIS and then go do your experiment, because EIS will give you a basic idea of if your electrode is good or your electrolyte is good, your connections are good, is everything okay. All of that can be understood by an impedance measurement. It takes a matter of 2 to 3 minutes, and with that, if you could go ahead and do your other characterizations, it would be easier for you to look into your materials and filter them as good and bad rather than waiting for your entire experiment to run. So this is another example of how you associate time constants and frequencies with different solid phenomena associated with your electrochemical process respectively. And moving on to data acquisition and analysis.
Madam, can I have
Yes.
one doubt, ma'am?
Yes.
If the series resistance or solution resistance RS will be same for if you are using same substrate, it will
Yes.
be same for all time,
Yes.
right?
Yes. Yeah, I heard you asked this question yesterday also. I remember. Yeah.
Ma'am, actually, that if we are coating, if we are preparing the material of a different concentration for such which will be getting optimized, which will be getting higher property like that, we are optimizing.
Yes.
In that time also, that series resistance and all is somewhat varying. What is the reason for that?
What is the range in which it's varying? Can you tell me the range in which it's varying?
Actually, ma'am, in supercapacitor applications, I am working. So
Okay.
in series resistance, it is nearly like in between 1 ohm only. Nearly in between 1 ohm, it is varying. That is, if you are 0.2 ohm, if you are getting for sample 1, then 0.21 or 0.25 for second sample, like that.
I think that is okay to to start with. I think that is okay, and provided if you would look at your OCV might you would be probably running your impedance at say for example the OCV, right? You are not going to set the potential and run your experiment. You're defining your OCV as a potential, and in that case probably your OCV is slightly fluctuating here and there, and probably because of that your RS is varying, and predominantly this 0.2 0.1 volt difference can kind of be considered as an okay value. That deviation is acceptable, I would say, because we are doing a lab scale experiment. So this much of a deviation is probably okay to deal with.
Ma'am, if we are analyzing all the samples now, so
Okay.
we are optimizing the optimized sample will say that it will have the lowest resistance, like so. On that basis, the series resistance is varying means somewhat it is not correct.
No, don't worry about the series resistance. Look at your, because it's a super cap. Okay. I would suggest you don't have to worry about it that much. Then if you would want to optimize it in terms of your capacitance. Don't depend on the impedance in that case. Probably that would be my suggestion. Because this much of a 0.1, 0.2, even 1 ohm deviation, I would say is agreeable on a lab scale system. Maybe for a pouch and a commercial aspect, that is not going to be the case. They're going to work with milliohms and all. But here in a real time analysis, I would say it is okay. And that deviation, I don't think you will have to take into consideration. You can look at your other electrochemical IV response and then judge your sample based on that, and rather not on the this thing. And you can also do your measurement at a particular voltage. You fix your voltage and then you try measuring your impedance and see if it's working or if you are getting any deviation in that regard.
Okay, thank you.
Oh, okay. So data acquisition and analysis, most of us are doing our experiments. So these are the different kinds of configurations that we have. Oh, we are already 8:30. So I'll just skip. So we have different configurations. We have CERE and working electrode, reference electrode, counter electrodes. These are different contributions that we can assemble and look at our systems. And before I finish, there are different checklists. So you can have linear, you will have to look at when you're doing your impedance measurement. These are the quick checklists that you have. You should have linearity, which means that when you are applying a perturbation, your input and output should be of the same frequency. That we may not be able to see on a one go, but you must make sure that your impedance measuring device is calibrated for that. And also your response should be entirely dependent on only the applied perturbation, and it should not have any side reactions or anything happening. And also you should make sure that your stability is there, as was the question asked earlier. So after running an impedance measurement, you can repeat your measurement and see if your cell is coming back to the original OCV, and you can see if it's not coming back, then there is something happened to it. It means that you have actually perturbed your system and you have excited it to another voltage. Rather, you have to make sure that it comes back to the original state. And one more thing is you have to see that it's a finite value. Just as I plotted, we did the maximum and minimum calculation, you must also have a basic idea of what the extremes are going to be like. Your lower potential, what would be the value? At your higher frequency, what is going to be the value? You must have a basic idea of it and then go ahead and doing your EIS processing. And this is a circuit description code. This is how you have to represent your. See, so for example, you have an R1, C1, R2, R2, C2, R3, C3, for all of them in series. This is how you have to represent them. In case if you are writing for a publication, this is a standard representation protocol. So anything that is coming in parallel can be put inside a brackets, and then they could be followed by a series term. Say for example, you have this, you can go from inside to outside. So you have an RC you have an RC parallel that is put in bracket, and that is in series with a resistor that can come in a square bracket, and this component is again in parallel. So this whole thing can again be put inside a curved bracket, and that in series with this R2 can come here in square, and this followed, it can go on. So one thing that I would want to say is, for a particular impedance measurement, you can have different circuits. Say for example, this impedance measurement over here can be fit with both these circuits, but it is up to you to decide to look back at literatures, see what kind of an electrochemical correlation that you can give, and then decide on your circuit. Say for example, you can add n number of components to it, but you must make sure that your circuit elements are restricted in number, and that each circuit element that you give in is associated with an electrochemical phenomena. Rather than just jumping in n number of circuit elements and trying to fit it, you should make sure that your elements are reduced in number. And this is one major thing that everybody have been telling if you look at an data representation. So you have an RC circuit and 1 kilo, 1 micro, this is what it's going to look like. So this is going to be a normal semicircle. And when you look at it, you must always make sure that your axes are equal. So you have 0 to 200 here and 0 to 200. One real-time centimeter is equal to 200 ohms here and 200 ohms here. So this is how your axis should always be. Rather, if you're going to plot it like this, you will do this because your impedance tail is going to be, your tail is going to be very high in most of your cases. And for you to show your tail, you will make sure that this axis is smaller and this one is very larger, and you will have a suppressed semicircle. So this is not acceptable. So it is actually like you're getting a semicircle, but in the first go when you're looking at it, it looks like a CPA element, and this is not how you're supposed to present your data. Rather, you can present it on the whole and then have an insert and show what's happening in a semicircle with the proper axis. So this is how you're supposed to represent your data. And when it comes to data acquisition, these are the input parameters. This is a biologic example. So you could have a sine wave, single wave, or multi-sine wave, and then you can say at what potential you want to measure your system, and then at what potential range you want to measure them. Different programs, different workstations will have different analogy, but this is the common input parameter that you're going to have. And then you can have measurements at 6 points per decade or 10 points per decade. You could have a logarithmic spacing or a linear spacing, and what is going to be your voltage perturbation. And then this is a delayed time, and then how much you want to average in. And if you want to do any drift corrections from the instrument, you can have this on. And if you want to repeat, you could give a value for repeating, and you could give a particular bandwidth in the current associated to it. So all these are the input parameters that could be done. And there are many circuits. I think for now, I might not have to teach you this, because I feel like you'd be familiar by now. So when you're fitting with biologic, you have ZView and many other softwares. We kind of use this. So you can, as I said, you can look at literatures, look at a corresponding or a meaningful equivalent circuit, add it in, kind of calculate your values and make sure that your chi-square is very less, and then see if they are kind of overlapping. So your spectrum and your fit should kind of overlap, and that is how you do your fitting. So how you fit, what element that has to be put in, I would not advise you on that, and I would say that that's going to be completely of your choice and your understanding of your system and how literature supports your material and your electrode setup and all that. That is going to be influencing you. So, but this is how you do it. You put in your circuit, you calculate and iterate, you look for components, and then you correspondingly go back and say, okay, R1 is going to be 1.1 ohm, R2 is going to be this much value, and you kind of infer and get information out of it. So this is the main outline, and thank you. So, if you have any doubts,
Hello.
yes.
Thank you for the nice presentation. I have lots of questions actually.
Yes.
You touched upon that fact that this electron transfer, when you're looking at the charge transfer, for the bulk, for the grain boundary, you see a different rate constant, and based on that you can get at what frequency you are getting your semicircle, and based on that you can differentiate.
Yes.
Can you give me an insight like how to think what could be the rate constant for those processes, and how you decided that for the bulk it will be at a higher frequency? Like,
yeah, usually when we look back at literature, say for example, I work on solid electrolytes. When I look for literature supports, I can look at how crystals are formed. Say for example, I have a crystal with no much of a grain boundary. I can look at just what's happening to the RC element and the associated time constant to it. So when you look at literature supports and review papers, you will know that they're ascribing different phenomena to different rate constants. They would actually provide you a range for it. Electrolyte ion transport will have this much of range. Solid electrolytes will have megahertz range, and charge transfer will usually come in this domain. So all of them are actually already been well reported. Any phenomena that we take are already well reported to have a time constant and a frequency range associated to it, and that's how we correlate it. It's mostly literature oriented.
okay, so suppose if you have two redox moieties, for just two simple redox moiety,
Okay.
and based on their electron transfer rate, you will going to get a different rate constant.
Yes.
And for one process, if it is slow compared to the other process, so for one process you will see at a higher frequency, and for one process you will see at a lower frequency. That's
Yes.
how you will get.
Yes, yes, yes. And you also have, I am not gone into details, you can actually calculate your rate constants from RCT values. Like you have an equation for it with capacitance and all that. From Randall's also you can derive it. So rate constants itself can be calculated from the values that you are getting from your semicircles.
Okay. And uh, in the constant phase element, when you talked about that semicircle height decreases, what
Yes.
does that mean actually, like physically? And also
Physically.
for capacitor, you said ki your
Mhm.
material is rough or something, then you
Yes.
will not get a ideal capacitor kind of thing.
Yeah.
But like for a charge transfer process, if the
Mhm.
semicircle heights decreases, then you can put the constant phase element, you said.
Yeah.
So what does that mean actually?
uh, Constant phase element actually means that uh, your electrode electrolyte interface, you are going to have a metal interface. So that metal interface is not going to be ideally plain or 100% polished interface. It's going to have some surface roughness introduced to it. So when your ion species are going to come, they're not going to go and plainly get attached to your electrode substrate, but rather they will kind of face an obstacle and a hindrance. So your equation for capacitor itself will change, and you'll have a Y naught factor associated to it. And that's how that Y naught factor will introduce a decline in It's not a depressed semicircle, it's actually a tilted semicircle, but it appears like the semicircle has been suppressed. So it's basically it basically has to do with your roughness factor, electrode roughness factor.
Okay, okay. And just one last thing about
Yeah.
the Warburg impedance, where you talk about this mass transfer thing.
Mm.
So, like, I'm having a hard time to understand based on the data which you are getting, how
Mhm.
you are imagining that these physical processes are going on. You get an, 45-degree angle thing, but now how I can imagine that it is related with the mass transfer thing, like
Mhm.
physically is do you can you comment or give some insight about that thing?
40, I will not have if you are getting an angle of 45-degree, I will not have any ambiguity. I will for sure happily say that it's going to be from a Warburg impedance. So I'm kind of sure that it's going to be so. The problem comes when it is when you have values that are not so when they're above 45, and that's when you get confused as to what should you actually put in and how should you fit it. Should it be is it you will have a doubt whether it is actually a straight line or is it part of a bigger semicircle. So all these concerns will be there only when your angle is not 45. But if it is 45, you are sure that it's going to be a mass transfer, and you can happily see what could be the physical equivalent for it. What is this? What is the system that you're working on?
uh I am basically working on some analyte species, like just the
Oh,
redox processes.
okay.
Want
So
to-
this the kind of the example that I showed you for the biology one, right?
yes.
So you have a redox active species also added to your analyte for measuring the impedance, or you just directly have your material alone?
So my material is actually pasted onto the electrode, and
Uh-huh.
whose redox the redox reaction is actually going on to the electrode.
Okay, okay.
So it's a
So,
kind of a storage kind of thing which I'm trying to do.
okay.
So
Which? Mhm.
for that purpose, I want to understand like this mass trans. I want to get some physical insight about the way you are seeing that this
Mass transfer.
imaginary impedance and the real real impedance is changing. You get
Mhm.
some uh, plot now. It's a
Uh,
45 degrees.
for
So
very
so how you are concluding that it is related to the mass transfer? So the physical thing I'm not getting in my mind. Like,
Mhm.
and
Uh, okay.
so
It's,
if something you can give insight, and one more thing in addition to that, can we get an insight whether which ions are diffusing or which species are diffusing with which rate they are diffusing, if this thing is related with the mass transfer
yeah.
thing?
You know what you've put inside your electrolyte. Like there's not going to be an extra component coming in. So if you're working on a system, you have an analyzed species, and that's going to be absorbed or desorbed onto an electrolyte. That's not, if it's an X species, it's going to be an X species, and it would either be converted or absorbed or reduced or oxidized. It's going to be one of these processes. So it is not, there's not going to be a Y or a Z component going to be involved. It is your system, your species, And one of those phenomena are only obviously going to happen. So there is no much of ambiguity when you have a single redox active species or a single analyte. Maybe for multiple ones, all those questions that you asked could come relevant. But as you asked for Warburg, as I said, if you have a material and it wants to go inside an electrode, if it has to travel through and if it has to get absorbed, and there is definitely a mass transfer hindrance that happens. If it's an electron transfer, it could easily have happen. But if it's a species as such, for it to go through the bulk of the electrode, there is definitely going to be a mass transfer difficulty, and that is physically interpreted through a Warburg. And again, this Warburg element can be equated to the porous electrode that I told you earlier. Warburg element can be represented in terms of a series of an RNC like this, and this again is a transmission line. So when you look at, if we could Google and see a transmission line in a Warburg element, you will find more of a similarity. If you, just as I said, I can also put it another way. For you to get a semicircle, you can put an R and a C in parallel. If you want to get a capacitor, you can put a C alone in connection. But if you want to get a 45-degree angle, the equivalent circuit that we can do is a series of R and C like this. If you have n number of R and Cs, like for example, you have 2, then you add 4, and then you add 10 or 15 or 20. If you keep increasing that, it would tend to approximately go after 3 or 4 sets of sequence, it will approximate to a 45-degree angle. So a Warburg in an equivalent circuit term is similar to something like this. So again, here also mass transfer happens, right? So you can physically interpret it as a combination of R and C, wherein your species has to migrate and travel.
Okay. And the second part, can we get information? Suppose in one case, one type of ion or something is diffusing toward your material. In other case, the other kind of ion. So can we get that insight also from this? Okay, which ions are moving or not? Like, is there any understanding like this lies in the literature or not?
With your understanding itself, if I could form a control experiment for you, you have one ion alone, you do the impedance, find out the rate constant associated with it. Second ion alone, do the impedance and find out the rate constant associated with it. Club both and find out what is happening when and where.
Okay.
From an external point of view, from now, I think that is how I can suggest a solution for you.
Okay.
Yeah.
Okay. Thank you so much.
Okay. Welcome.
Yeah, good
Hello,
evening,
ma'am.
ma'am. Hello.
Good evening, sir. Hello, sir. Yes.
This is Ramesh Goswami from CSR IIP.
Hello, sir. Hello, sir. Nice to meet
Yeah, ma'am, I have some doubt. Basically, I'm working on corrosion. So, for the analysis of the EIS data, first we run the OCP and we
Okay.
get it the some open circuit potential. So, for the EIS measurement, we put it the 1 lakh hertz to 0.01 hertz. And
Okay.
so the potential should be with respect to reference, yeah, with respect to OCP. So in the both case, when we put it the with respect to OCP and when we put it the value with reference, we get at the same curve. So what is the difference between these two terms?
So, sir, you're working with a 3-electrode system.
Yeah, yes, ma'am.
So you're working with a 3-electrode system, in which case your OC, when you say your mesh, what is the, I can understand OCV, but when you say reference, what is it actually meaning?
Yeah, reference is electrode, that means SC, saturated calomel electrode.
Oh, okay. But I would rather suggest, I have never seen people running it at the reference potential, but rather whatever is the OCV, if you could run your measurement like that, that would be the actual value rather than your reference value.
Yeah,
It
suppose.
has to. So
Yes, ma'am.
whatever is your potential, say for example, you have a working electrode, you have a reference electrode, and you have a counter electrode. The potential, the OCV that you actually say is actually measured by the potentiostat to be the potential between the working and the reference electrode. So this potential difference is what is seen to us as an OCV. And at that OCV, if we do impedance, I think that is more realistic.
Okay. That means we should to put the potential we get it from the OCP and then with respect to OCP.
Yes. You will also have, what is the potentiostat you're using?
Versa state 4.
Oh, okay. I'm not so familiar with it, but you will actually have an option to run your cell at an OCV rather than giving an voltage. So it will be like E equal to, it will give you a value and it will say with respect to reference or with respect to OCV. Oh, okay. So if you say you can actually have E equal to 0 with respect to EOCV, which means whatever is the OCV's potential, I want my impedance to run there. I can show you this. So I think I've got your doubt. So this is what you asked, right? So you will
Yes.
set 0. So you will set 0 with respect to EOCV.
Yeah, yes.
So you will set 0 with respect to. If you are putting E reference, you have to reverse calculate what is the potential difference. So I would suggest doing this.
Okay, that means only the zero. We will put the only the zero and
Yeah.
with respect to C. So what is the
Yes.
meaning? Suppose that the mild is, suppose in case of the mild steel, so the mild steel having some potential. So what is the effect of the mild steel? Suppose we put it the zero with respect to OCP. So there is no meaning for, because we cannot be compared with, this is the mild steel aluminum and this is the stainless steel. So there is no meaning. Means suppose if we put it the with respect to OC and the put it value working electrode is 0.
0. Okay, so I'll tell you now. When you say OCV, it's actually right. You have a system. You have your working electrode, be it mild steel or whatever system it may be. You're putting it inside an electrolyte, and you're able to sense a potential. So that potential that you're saying is the open circuit potential. So for mild steel, the open circuit potential can be different, but for your other material, it could be different. Say, for example, you have 100 millivolt for this, and for the other one, you're getting 120 millivolt for it. Be it 100 or 120, these two systems are in their respective equilibrium potentials. So for you, if you are able to not disturb them, if you want to measure the second system at 100, you're actually perturbing it and going into, you're kind of moving it away from your equilibrium. So rather you don't change the potential, allow them to be wherever they are. So EOCV is their comfortable position. So allow them to be at EOCV itself, their own equilibrium potential, and 0 versus EOCV is that stay at EOCV. If you're saying move to 20 millivolt versus EOCV, if your EOCV is 100, your measurement will be done at 120 millivolt. So don't do that. Rather, if it is 0, it is going to be at your EOCV itself, and then you do your impedance measurement.
Yes, ma'am. Yes, thank you, ma'am. One another question that suppose suppose we get at some EIS curve. So what is the parameter that we fitted the because we have different type of the circuit. So which circuit is fitted for the, because the in case of the chi-square value is minimum for the fitting. Okay, so what are the parameters that we choose the different type of circuit?
Okay, I can get that. Say, for example, I have a impedance plot. I will show you. Say, for example, let this be my impedance plot. Okay,
Yes,
I can actually represent it in multiple ways. Say, for example, I can just put a Randall circuit, an R and C in parallel, and then a Warburg associated to it. I can have that as a circuit. I
Yes,
can
ma'am.
also have another circuit with one solution resistance and multiple RC circuits, and again Warburg attached to it. So this 5-element circuit and this 15-element circuit, both of them will fit this Nyquist plot. Both of them will give me good chi-square value, provided the higher one could even give me better chi-square. So adding more elements to your equivalent circuit might reduce your chi-square value, but your explanation, you will not be able to give an explanation to it. So you actually try to minimize your circuit elements and try to get your best chi-square fit, and provided for every system that you're working, say for example you're working on corrosion, there will be a standard set of protocols and explanations given in your literature support. It is always better to have them as a reference and fit circuits accordingly. The values might be different, but the kind of physical interpretation that you're going to give will be similar. So it's better you minimize your circuit elements and have a proper physical interpretation for it, rather than kind of trying to reduce your chi-square.
Yeah, ma'am. One other question, ma'am, please. Last question is that
Yes,
suppose in case of the in Bode plot, we get it first. We get the higher frequency is a very straight line, and then is to down. Can you
Okay.
can you please show the board plot? Yeah, this is a blue line. Suppose that in this case where the R naught and R1, this is a straight line, and when is a turn is very turn and then straight. But in some case the where the R0 and R1 start, it's toward higher, and sometimes it's to tilt towards down. So what is the reason that?
Okay, these are actually theoretical circuit fittings. Probably when you're fitting, you're going to fit it with not a C but a CP. We have not looked at the constant phase element or the Bode plot of a R. You have a C here. If you have a CP here, it's not going to be a straight line. Probably that is why you're getting an inclined slope rather than a straight line here.
Okay. Yes,
That could probably be the reason. I'm not 100% sure, but that could probably, because we usually we are more comfortable with the Nyquist representations. We don't go to the Bode, so probably.
Yeah, because the Bode is a total impedance of the real. That means real
Real and
imaginary.
imaginary, yes.
Yeah. So in our case, we need a total impedance. So that's why the curve tilted towards the higher and towards the down. So some viewers ask that what is the reason behind this. So there's a question.
Oh, I am not sure. So probably if I could look at your system and if I'm familiar with more of your examples, probably I'll be able to comment on it.
Okay.
So
thank you, ma'am. Thank you so much.
Yes, sir.
Ma'am, I have one question.
Yes.
While taking the AIS measurements,
Mhm.
I just got a very large fluctuation in the high frequency region. So what
Okay.
is the reason behind this?
High frequency region means over here, right?
Yeah. Yeah, yes.
Okay. Is it happening for all your systems or only for one particular system that you're using?
No, I checked that on a different instrument also. There is also some fluctuation I
Okay.
see.
Okay, I'm not sure of what. Probably, if you could do some drift correction also in your AIs, probably you can see if that is getting corrected. And what is the sine perturbation that you're using? Sine wave perturbation?
Just I will use it for the supercapacitor already.
Okay.
Yeah,
Probably
and
supercapacitors will actually give us a neat profile. They're not going to trouble us in any way.
okay.
It must probably maybe because of your coating or something else could be an factor. And
Okay.
to what frequency range you go, I don't know. No, that is also not going to affect. Probably maybe you can ask somebody else to repeat your experiment and see if they're also getting the same value. And you can also check your EIS instrument. You can take a breadboard and do a simple RC connection and then keep your working electrode and reference auxiliary across it and do an impedance measurement and check if your channel is working good and try to calibrate it. So just one cross reference. Otherwise, it could be due to some experimental error from our side, probably.
Okay. Thank you.
Welcome.
Hello, ma'am.
Yes.
Your presentation is very nice. So you touched the all basic things.
Thank you.
I am new to this topic, but I understand a little bit. So still, you because of time limit, you are going fast. But you that experimental party is not showing in your overall slides. Only that is like I think.
Oh, okay.
The minimum point, but you will show one like 3 electrode system. This one,
Experiment is nothing, but you just put
so,
your.
ma'am, I will ask one question about this. So, how this electron is transfer, like in two electrode system, we can tell ki the electron is going from anode to cathode. So that electron path, I want to know in 3 electrode system.
Okay. So I will give you this example. Ignore this WS part. Okay. So you have a counter electrode, a reference electrode, and a working electrode.
Yes.
Okay. So when you're applying a potential, you're going to apply a potential. I can show you a circuit. I think I have a. So okay. This is what it is. When you have a 3 electrode system, it's your working electrode, reference electrode, and counter electrode. But when you have a 2-electrode system, it's a working electrode and an auxiliary electrode, which is combined both. So you want to know what's happening here.
Yes.
The point is, this is your potential extent is going to look something like this. It will have control. I'm not so familiar with how these works, but I can give you a basic idea. So you have your container, you have your working electrode, you have your counter electrode, and you have your reference. So when you're applying a voltage, say for example you're running a CV, so if, for example, you want to charge your battery or something from this voltage to this voltage, you are going to apply a potential to this working electrode with respect to your reference electrode. So this reference is something that is going to be there stationarily. So it's like it's going to be there. So with respect to this reference electrode, you're applying a potential, and you keep applying a potential. And when you apply a potential, say for example,
Oh. Hello.
It seems Madam has some network issue.
Yes.
Yeah. Madam? Hello, Madam. Yeah. Yeah, I think she has some network issues. In that case, anyway, Madam will continue tomorrow and after tomorrow too. So in that case, is that okay to shift our question answer to tomorrow?
Yes, sir. No problem.
Yeah.
Yes.
So in that case, yeah, I think she joined. Madam, you are muted. Can you?
Oh, there was an issue with my login. It gets off with time, so it's probably 2 hours, right? So that's it. Okay. So what were we talking about? Yeah, I'll share my screen. Yeah, so I have a battery material that can charge and discharge, and it can have a potential. It can charge or discharge at a particular potential, say for example 3.4 volt. Initially, when you are assembling a material, so you have your material coated onto your electrode, you have a suitable electrolyte, and you have a reference also. So what happens is, I kind of, this reference electrode is a material that will not change its potential with respect to anything that is happening. So its potential is always going to be kept constant. So any reaction that's happening will happen in the working electrode. You apply a potential, say for example, it goes to 3.4, and at 3.4 volt, your active material can start oxidizing or reducing, and all that electron transfer can happen here. So electrons can come from the external circuit, get involved in the reaction process, and from the counter reaction will also have to happen. Say for example, there is a any reaction will also have a counter reaction to happen. So that counter reaction will happen in the counter electrode, and that counter signal, if we want or if we don't want, we can ignore that. So you have a reference, you have a working electrode. Any reaction, electron transfer will happen here and here. If electron is coming in from here, it was again coming outside. So these are the two systems where an electron transfer happens, and whatever current change is happening, that current change is measured across this, and the potential change is measured across your reference and your working electrode. So that is how it is usually done.
So you use counter reactions. Give
Yeah,
an example one like Fe3, Fe2. That example.
Sorry?
Little bit. Can you explain that Fe3 and Fe plus 2?
It's a battery example. I think you can look at it anyway. You have a species. Say for example, the species is oxidizing. Say for example, A is getting oxidized. So or A can get A plus E and form an A minus. So A minus can be formed here and the electron can be coming from the other electrode. It's just that what you need will come from the other electrode, and what is taken up will be taken up from this electrode, whatever be the couple.
Okay. Yeah, this picture is looking like very nice. Yeah.
Yeah. I heard this question yesterday, so I just had it as a backup. So.
Yes, I'm very thankful.
Yeah, okay.
Yeah.
Anything else?
If we don't have other questions, then I guess we can wind up the session.
Yeah. Okay.
Somebody is asking something. No, I guess. Anyway, thanks so much, and it is very informative session.
Thank you.
And you started from the very basic, and you maintained that flow too.
Yeah, thank you.
And it's a wonderful session.
Thank you.
Thank you so much, and
Yeah.
we'll continue the same thing in tomorrow. And yeah, that's it.
Yeah, thank you. I'll try to reduce the time for tomorrow. Sorry that it took this long. I didn't know how long it will take. So sorry for that.
We never felt it was that lengthy one. It's very nice to hear you.
Yeah, thank you.
Yeah, the explanation that you gave to all the ways that you put even the pictures that you put and the calculation you made, all the things are really nice.
Thank you.
Thank you so much.
Yeah, anybody, if they have any other doubts, I could see a few questions in the chat box. Maybe they can write to me, to my mail ID. So later sometime.
Yeah.
Or the third session we'll have time. Probably I'll have only a little to, maybe EIS data acquisition also we can discuss some more in the third session, the day after.
Yeah. And one more thing, in your material, the PPT, you showed some YouTube link. So if you can share that one.
Okay, probably by WhatsApp, or should I share it by chat box?
Anything.
I'll share it by WhatsApp with you.
Then okay, then I'll share with all the participants.
Okay.
Thank you so much.
Okay, pleasure. Bye.
Yeah.
Thanks. Bye.
Okay then. See you tomorrow.